All right, we'll get going. My name is BRECH. I work in power systems for IBM. I'm the CTO of solutions, and my job varies everything from stuff we do in firmware, new accelerators, to new software on the platform, and how we make advantages out of it. So, obviously, I'm going to talk about crowd here, but we'll start off just. So, businesses today, the customers we talk to, all they say is, hey, all this data, I'm relying on it to drive my business. Okay, I'm changing the way I'm doing things, but it's all about efficiency. And I always put time first. Everybody jumps to cost. But I will tell you that most of the CEOs, CTOs, CIOs that I talk to say, time is what I'm really trying to do. I need to react fast. I need to be able to change things. I need to be able to do things fast. I need to be able to make decisions in what I'll call quasi-real time, because real time means something different to everybody. But that's what I'm about. I want efficiency. Now, of course, efficiency for cost, efficiency for consistency, all drives to the bottom line. But number one for all of them is time reduction. The second thing that's interesting is better insights, broader sets of data. How do I leverage all these things and drive more accuracy and more speed in my decisions? And so I'll give you an example. We were working with a retailer who came in and said, you know, my marketing campaigns take me 6 to 9 months to develop. I want to figure out how to do it faster. Because things change from when I start to when I actually roll things out. So we use analytics, both sides of the equation. On the engagement side, what they did was they ran some ads at a major sporting event, and we mined Twitter feeds and a whole bunch of other things to see if there was any reaction. Okay, the ad said nothing about price or sales or anything, it just talked about the product. Okay, it happened to be a perfume. At the same time, we were running analytics on their core data of their customer loyalty program. People that buy this, what else do they buy? What does my inventory look like? What is my price elasticity so I still make money on this? How long does it take me to refeed my stores with product? So what's my supply line? And they took all of these, they ran the ad, and over the next 48 hours we did a bunch of churning on all their data and came back and said, okay, here's what the market messages tell us from outside. Here's what we learned from your core databases. What do you want to do? And so within the next 24 hours, they decided on a marketing campaign. And 24 hours later, they sent emails, or text, I think it may have been both, to all their loyalty customers and said, hey, we got this great special. Come on in, you can go online and order it, here's the code. You can go into the store and pick it up, here's the code you use. And then they mined the data, because the codes obviously were there, that we could mine to see, hey, is it going over big? Is it not? You know, what adjustments can be made to it? So they ran that for 48 hours. And then said, okay, now we want to make an adjustment. And they watched this, and then they decided, okay, now we have it down, and now they rolled it out to all their stores. So they did all the print ads and the posters and all the things that went into the store. But they waited until they knew what kind of reaction they were going to get before they did that, so that they could target it at what they saw happening. So within a week, they had a marketing program that had real-time analytics and real-time measurements of what was going on. Okay, they called it real-time. I said quasi-real-time. I used to work on real-time systems for missiles. It's not 48 hours, 7 days is not real-time to me. To them, it was a huge change from 6 to 9 months to something they could do in a week. They could react, test, adjust, and roll things out very, very fast and efficiently. And do it all based on real decisions, based on real data. So what that's led to is, we all know the amount of data is exploding. All right, whether you want to talk about IoT, whether you want to talk about all the stuff going on at Twitter and Instagram, everything that's going on, the amount of data is exploding. And that leads to a little bit of a problem, all right? We had analytics that worked to a certain degree, but now we just super exponentially increase the amount of data. Well, how do we get through it faster? Because they want to do it really fast. So, and the other thing that changed is the type of data, right? You know, it's not relational database, row column data. It's not just transactions. Yeah, that's important, but they're looking at all kinds of different data. A big thing that a lot of them are doing, that we're working with them on, is data authenticity. Because, hey, if I'm going to trust this data, I really want to know where it came from. I really want to know if it's accurate data, or if somebody, you know, created some bot out there that's, you know, feeding me garbage. Okay, because they're making real business decisions. And so it comes down that they have this problem, massive amount of data to ingest. Okay, with some clients we're working with, we're talking billions of records, which it's kind of large, but then I have to analyze it. I have to act on it, make decisions. Use my analytics to make decisions, measure what those decisions meant to my business, learn from different things that are going on, and then optimize it and go right back to the cycle. Because I have real data that I can act on and make decisions and keep testing and feeding it. You know, we talk a lot about agile development, agile applications. You know, this is kind of an epitome of that. You know, we're making adjustments as we go. We learn new things. We learn new insights. We adjust some of the questions we ask. And so this is really kind of a problem. The amount of data I have to look at is growing. The amount of time that I have to look at it to make real decisions is shrinking. And you look at that some days and you say, is this an impossible problem? So you got to take stock and back up and say, okay, how do we address these different pieces? And I'll show you some of the things that we're doing. So when we talk about graphs, right, you all understand graphs. Graphs are really critical. Graphs probably have even the hardest time, in some sense, dealing with real data, because it's not just a record that changes, it's how that record changes and how it relates to everything else that I have to refactor before I can make decisions off of it. So it becomes, even while a graph is really good at seeing those things, the problem becomes, how fast can I do it? How big can I do it? How big can I build graphs? And when we looked at some of these things, we found different things scale differently. And so we attacked some of those problems. But we see all kinds of industries growing. I put one extreme example. Can't tell you who the customer is, but they have a 30 terabyte graph database today. They're bringing 25 gig of information ingress every day. They have 400,000 updates that they have to make every second in the database. 60 billion relationships, and the rule is they need to do all that in less than 200 milliseconds to call it effective for their business. Quite a daunting problem when you think about it, right? So as we looked at these things, both for the graph database and the work we've been doing with NEO and some other databases, we looked at exactly what those problems were with clients, what they were trying to do, how we needed to adjust for where they wanted to go. And I'll explain a little bit more about that. The other thing that we have to remember is, as I said before, the traditional core data is just as important as all the new data, right? If I don't know, how can I do a real marketing thing if I don't know my loyalty customers, I don't know my inventory, I don't know my price elasticity? I have to factor all these things in to making a real coherent business decision. Okay, so it's not just all the data on the right side, it's all the data on the left side that has to be gone through to find insights. And basically it's all about, as I said before, ingest, analyze, and act. Okay, made it simpler around here because I could make it big enough so you could read it. But that's really what everything's about when we start talking about how do I use these databases, how do I use data at a massive scale for business, for real-time business results. So you're probably wondering why Power is here. Who ever heard of Power before? Power architecture. That's pretty good for a room like this. Oh, okay, earlier today. All right. The thing that's interesting is Power has been around for a long time, bitch-driven enterprises. We built very big systems for very big enterprises. We didn't build smaller engines, but as we found and looked at software, the drive was to leveraging smaller engines. So when we were first designing Power 8, we said, well, what are the applications that we really think are going to be key over the next 3 to 8 to 10 years? And it revolved around data analytics. And so a lot of what we did in the chip was based on analyzing applications that did big data. We sat and tore through them all, and every time I saw the processor in a wait state, whether it was on a Power or an Intel box, we said, oh, there's a problem here. We got to fix it, because nobody likes paying for a processor and then finding out that a third of the time it sits waiting for data, right? It's not very efficient. Okay, so we did a lot around that. We had the issue around cloud economics. People didn't want just big boxes. They fit certain environments and needed to have a range. And quite frankly, the client that drove us here was Google. Okay, because the way they lay things out in their data centers, they wanted to leverage power, but they said it has to fit into our structure. And so it was a big factor in how we designed power. And the last one, and to me one of the most important, is open innovation platform. We recognize, you heard Doug this morning, if you heard that we recognize we can't do it all on our own. Okay, there's too many unique things going on, too many small businesses that have great ideas. How do we help them bring it to market? How do we do things to really make those things commercially viable? And so that became a big focus of what we did and how the Open Power Consortium started. It initially started with 5 companies: IBM, Google, NVIDIA, Mellanox, and Tyne. Those were the original 5 members of the Open Power Consortium about a little over 2 years ago when it started. Now there's many more. We'll come back a little bit to that. So why is power good for these things? Well, we found that analytic applications love threads of execution. They love real threads of execution, not just solver threads of execution. So the power processor can run in SMT 1, 2, 4, and 8. Okay, you can run all those SMT environments in the threads, and with SMT 8 in a 2-socket, 2U box. Each of the cores has, or each of the sockets has 20 cores. It's 192 threads. The first software analytics guy always said, here's a box, scale your application up. You like lots of threads. He goes, well, how many are in it? 40? No, a few more. How many? 60? Nah, keep going. When he got to 192, he was like, no way, you can't do this in a 2U box. It's impossible. It's probably not going to work very well. He ran it, came back and said, how do you do that? So it was a focus of our design to give you threads of execution, because that's what helped you have better software to deliver better business outcomes. Memory. 4x the amount of memory that you can put on this box, 4x the bandwidth. We can drive our memory interface at just over 400 gigabytes per second peak. We can run it sustained at about 230 gigabytes per second. My challenge to you is find another system that can keep the processor fed that fast. We'll get to cost. We'll come to cost. Cache size, 4x the amount of cache. Our architecture around memory is a little different, and I'll explain how that comes in. But these are the things that happen. Now, quite frankly, when we first put a chart like this together, there were 4 columns in it. It had I/O bandwidth that was 3.72. The marketing guy said, we like the 4s. If you can't get it to 4, take I/O off the chart. But I/O is critical. I/O is critical. And if you heard Google talk about why they're using power, it's about the bandwidth of memory and the bandwidth of I/O. That's what they're using. A bit about the consortium, the ecosystem we have. I'll show another chart with a bunch of logos on it, but unless you find something that's really interesting, it's not super meaningful. But we have people, another change, I should say, that was made in Power 8. Through Power 7, if you wanted to run Linux workloads, they ran in Big Indian mode. Big Indian, nobody does Big Indian anymore, only mainframes. Power 8 supports Little Indian as well. Actually, it's been in since the pre-Power 4 chip, because we were doing it as part of a joint project with a big software house. They decided to do something different. We kept it in, we've always tested it, we've just never opened it up. So we opened it up because the feedback we had from ISVs is one of our hurdles is switching from big to little Indian, or little to big Indian, I should say. Okay, so that's where a lot of that work has happened. We do tons of work in the open environment on Power, and you'll see some of the software providers on here and on the other chart. The collaboration, as I said, we've done things in the chip based on people that came to us and said, I want to use the chip, but I need this. How can we fix this problem? And so we designed things together. It was a real interesting thing. IBM before never had really open hardware architectures in the sense we never opened up our processor designs. We actually tried to do it twice before. On Power and the corporation, the board said, no, that doesn't make any sense. So when we went back for the third time, Brad McCready, who was my boss at the time, we put it all together and he took it to the board. And I told Brad on his way out to New York, I just want a text. Show up Monday or not. Because I wasn't sure if I'd have a job come Monday morning. 3 times you're out, right? They went for it. They said, go and make it happen. And we've been working on it since. And we'll talk a little bit about that. Our naming structure, as Doug said this morning, is really unique. Power 4, Power 5, Power 6, Power 7, Power 8, Power 9, Power 10. People understand Power, so we keep using it. It's just not very creative. So maybe we'll fix that someday. So what were some of the other things we were trying to do? We recognized that we were coming to an end based on the laws of physics. If anybody has a way to build a substrate that's less than 1 atom thick, come and tell me, because we can make lots of money. If you can split atoms without blowing up the system, we can make lots of money. And that's really the problem with technology. We've shrunk and shrunk and shrunk, and in the beginning when we did shrinks, we get 70% performance improvement, 85% performance improvement. The last couple shrinks across everybody's processes, quite frankly, we tried and scraped to get past 15%. The technology doesn't allow it. Okay, gates can only get so small, atoms can only be so thin, and you know, when you get too thin, you have leakage current, so you start drawing a lot of power and not getting anything out of it. Just lots of problems. Now, we looked at other technologies. There are other technologies out there we can get smaller. The problem is, whether it be graphene or some of the other substrates, none of them are commercially viable. And quite frankly, we don't expect any of them to be commercially viable for at minimum 5 to 8 years. The fabs, just to get down to the latest one, cost in the range of $23 billion. It's a big investment. And the technologies themselves don't scale to volume, which means I can't make a business case. I can make them work, but I can't make a business case out of them. So we went back and looked and said, well, what are we going to do? Customers expect, price performance increases every cycle. Well, we went back and took a page out of our HPC designs, and we brought accelerators. But when we first started looking at accelerators, we saw the problem with accelerators. I have this great CPU with all this data. I have this accelerator that can really churn on that data fast to come up with an answer, but I have to move the Colorado River through a drinking straw. The I/O bus is just way too inefficient to really make accelerators work. So I need an accelerator that's 14, 16x what I can do in software to justify commercially using it. And so we attacked that problem, and we'll talk a little bit about that. So there's really three important things to understand. I'll show you a diagram of the buses. The first one is a bus that we put on a chip called NVLink. Gee, it's hard to figure out who did that with us, right? NVIDIA. Basically what it is, it's to coherently attach a processor to the GPU. Okay, and it does it at 40 gigabytes per second. So all the overhead in the I/O path, which depending on which one you look at, is anywhere from around 32,000 instructions on down, comes down by a factor of 10. Okay, a lot of inefficiencies come out of the system. We did the same thing on CAPI. And CAPI is another one of these unique IBM acronyms. It just stands for Coherent Accelerated Processor Interface. Okay? Basically, it's the same environment, but it uses PCIe electricals today. So it's a 16 gigabyte bus, but without all that overhead. They're all part of the coherent memory structure. And so that's where you get the efficiencies. You get all that overhead out of the way, so you can really use the processor and not have the processor waiting on things. Okay. The last bus is the memory bus, which is called DMI. And basically what happened is we were looking at memory technology. I don't know about you, but over the last 5 years, you know, whether it's Samsung or whoever said, hey, we're going to have bubble memory, 18 months. Oh, we're going to have photoresistant memory, 24 months. I still haven't seen any of them that we can produce and scale. Okay, the technologies are there, but we can't produce them in scale. Nobody can. So as we were looking at this, we kind of hedged our bets a little. In the past, the memory controller was either in the processor or in a separate controller with another bus. What we did so that we could still do coherency and all the things we wanted to do is we split the logic. A good portion of the logic's in the processor. There's a little bit of logic on the memory cards. Okay? And what that allows us to do is, hey, we create another version of cache, but it allows us to drive those data rates. And if any of these technologies come along, every one of the major memory companies is using that bus to test new memory ideas today. Okay, so a really cool, big, cheap memory comes along, we can take advantage of it without having to respin the processor. Okay, so those were the two things that drove us there. Bandwidth, cache was a side value, but the ability to bring technologies to our customers faster. So, how are these being used? The NVLink with the GPUs together are doing tons of things right now. Weather, there's a bunch of defense applications. We have some databases running in there, Connecticut, running in there, or GPUDB, for those who didn't catch the name change not too long ago. Financial services things, biosciences. An example, well actually it's down the next one, I'll give you an example. The next one is using CAPI technology, which typically is putting the algorithms in Flash. Okay, not Flash, FPGAs. Okay, if certain algorithms, you can really speed up an FPGA if you use them constantly, and that works. Just an idea in the financial realm, we're working with one financial customer, and they do a lot of projections using Monte Carlo simulation. So we put a Monte Carlo algorithm in a card and said, go see what that's for you. Going into it, they said, well, if you can give me 5 milliseconds of speed faster than finance the house next door, it's probably worth about $500 million to me every other day. Cool. So they tested this. It ran 250 times faster than the fastest box they had. And I tried to get 1%, didn't work. But what we found, though, is all financial institutions have slightly different Monte Carlo simulations. And so we're working with them in a way that they can personalize them for their use. Okay? Because every one of them doesn't want the same exact thing. Which, hey, RPGs make it a little easier, right? And so you'll see different algorithms there. We've stumbled across, and what's made it exciting to, as Doug said this morning, to still be in hardware, is we keep stumbling across new applications. One that we're still talking with, I live in Rochester, Minnesota, home to Mayo Clinic. A couple years ago, they were putting proton beam treatment in. And because I knew somebody there, I got to sneak in on one of the tours. And I said to him after, I said, so what's the biggest problem you have with proton beam? And he said, well, it's such a fine beam, which is great so that we don't kill healthy tissue, but aiming it is a challenge. And typically what happens is they put a patient in, they think they got it right, they do it, they look at some scans and go, dang, you gotta move it. It takes them 24 hours to redo the targeting. Now, the patient's not gonna sit in a proton beam modal for 24 hours waiting. So now they have an extra problem. When that patient comes back, did they get him in the same exact spot that he was in before I did the retargeting? Very hard to do. We found, he goes, and we use Monte Carlo simulations to do that. And the little light went on and said, ding, 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 we should talk. And so they're investigating how to leverage that acceleration. And right now, they're saying it probably cuts our 24-hour cycle down to less than 10 minutes. I can ask a patient to stay in there for 10 minutes. So it drives their costs down because they don't have all this in and out, and gives better patient care. So lots of cool things we could keep coming across. Well, let's talk a little bit about Neo and what we did with Neo. So when we bring new software to Power, a lot of it comes from Linux, Intel, x86 environments, so it's a little Indian. You can just recompile it and run it, and it'll run. But I will tell you, the first recompile and run probably isn't going to give you the result you want. And the reason is, as we dug into it, okay, I wrote a lot of code myself. And coding guidelines were always a challenge. How can I get more out of this software if I get rid of coding guidelines? And we find that's what happens in a lot of software. We find software that's tuned specifically for the cache of that specific processor. And so even if they're going to a new processor in the x86 family, they have to readjust it. So we have tools now that when we have ISVs come in and say, hey, I want to try that stuff on Power, we can help them do the port, we can help them do the optimization. We have tools that scan the code and look for the things that we found over the last 4 or 5 years as we started down this path. So we kind of call, I always call the stages port, optimize, which is take advantage of the architecture of Power, okay, and then accelerate, which is where we start adding accelerators into the equation. And all the companies that we've worked with, we've gone through the same process. So what we did, because Neo, like some other databases, loves memory, but sometimes, it doesn't scale as well when I have to do lots of nodes. Now there's some clustering stuff that he talked about today that will hopefully address some of that. But because, as I said before, whenever a record or an item changes, I have to go through and rebuild all the connections, because it's all about connections graph, right? It takes time. So what we did is there's actually 2 configurations. The first one on the left is the first one we delivered, where we put a CAPI card in the slot. It talks fiber channel links to a flash array. It allows you to put 56 terabytes of extended storage right off the processor, directly owned, maintained by the application. There is no calls to kernel or anything else. You own that space. And we have drivers in there that they compile right into the application to do mostly block, single block, put get, and some management around it. There's also a set that we did that Res uses called NV, and it's really about trying to help them maintain pages. They wanted to do something different, so direct block didn't work. There's acceleration above it, and then it uses the block interface. Okay? We recently came out with an internal card, because some customers said, well, I want to prototype this, but geez, those arrays are really expensive, man. Can't you do something? And by the way, when we put stuff in the data center, we really like the idea to fit in the box. So we delivered a card, excuse me, that basically has 2 terabytes of flash on it, CAPI attached. The latency is better, obviously, because we're not going to cross the bus, than the external one, but it allows you to do 2 terabytes. So it's additional above whatever memory you have in the system, but the application owns the space. I don't have to worry about, oh, a file system. Hey, if you need a file system, you put a file system, you go. But if I want a block, I don't have to go through all those headaches, all those task swaps in the processor, which cut into your efficiency. And that's how we did it. And so anybody that wants to can go look at that code. It's all open source. It's all out on GitHub. All the documentation's out there, and so you can take a look and see, hey, does this fit what I'm trying to do? Some people ask for a comparison. So what you have here is 4 different ways we ran this environment. So CAPI NVMe is that flash internal card that I mentioned. Traditional NVMe is a PCI attached NVMe card. So a traditional NVMe card comes from several vendors. The third column is a direct I/O environment that we created basically for test. But we have some people playing with it and using it. And then the last one is traditional storage. So actually the third one is the external array. The last one is SSDs in the box to try and get a comparison. And so you can see from an SSD environment down to a CAPI environment, I have 21% of the overhead in the environment to move data. I always tell my team, hey, I'd like it to be a lower number, but if I was investing 21, sounds pretty good. If I get 21% return, I'd be happy. That's how we did it, and we did this just to show you the differences between them. The bandwidth difference, you'll see, I'm sorry, this is a CPU thread. So this is really a view of latency. Okay, so we use the NVMe card as our test center point, so that's one. The fiber channel card, actually, that should be different. But it's how many relative IOPs, IO processes, that I can do. So the fiber channel, standard fiber channel, to the CAPI attached fiber channel, to the internal CAPI NVMe. So you'll see, I can drive 3x, 3.7x more bandwidth, more IOPs through the interface. Because I get rid of all that overhead. There's no real magic here. It's just getting rid of overhead. Getting rid of the things that processor designers hate to see when they look at runs. When a customer says, gee, it's not performing the way I wanted to. Oh, well, look at this lock you have here that's holding for all this time. Or look at all these times we're waiting for data. So, from when we started this, our goal was to take Neo4j, which we saw as a predominant graph database going forward, right? I'll talk about a lot of the cool things they're doing. And when we met with them, we said, hey, we really think you got a good path here, but we think we can make your path better. And I can remember sitting down with Johan the first time, and he goes, I'm going to start changing the code now. And so he started changing his code to use this before we had this ready, which was an interesting thing for test. But he was really excited about what he could do with it. And we really think this provides an unrivaled scalability and performance for graph databases. We have some customers that we've talked to with Neo that have really big databases and have problems as they scale them. And so they're really excited about getting this code. Some of them have been playing with, but it's really cool. Basically, we got a lot of Here's the view. Basically, you get 82% more throughput than a Broadwell on a per core basis. Now, we did it on per core because, quite frankly, if you have tons of cores in the system, you can saturate the bus. Okay, so the overhead kind of disappears in a sense because you're using a whole bunch of cores and threads to do garbage work. But if you really want to run your application, we can give you those processor cycles back. Power in and of itself, as I mentioned, we will do both scale out and scale up. Our bigger systems, you can put 32 terabytes of memory, main memory in them. You can also work to extend them. And all the way down to our 1U boxes. We have CAPI in, although it rolls out testing on different boxes at different times from our test organization between us and DM. And so you have to look at which box it is. That's kind of the end of what I wanted to say. Give you a little bit of description of power, the technology that we're driving, how we're leveraging it with ISVs and customers that want high-end applications. When customers say, well, wait, you have all this enterprise stuff in these boxes. Is it down in these boxes? Not everything, but more than exists in our competitors' boxes. Okay? Just because of the way we're doing it. Some of those boxes at the low end are built by companies like Tie-In, Supermicro, and whatnot, because their customers, some of the big data centers, really tune of what's on there. If I don't need that resistor, get it off. It costs me a half a cent.
Is it still be separate from, say, Bluemix or kind of focusing on Linux?
Right now, Bluemix today, if you look at Bluemix, there's really 4 parts of Bluemix. There's all the tooling, the UI and all the tooling that you can do. There's the orchestrator engine. There's what I'll call near microservices and other services. Okay, you can use Power in other services today. Okay, we do not run Bluemix on Power Processor for the development and the other pieces. We like to, but we're working with our cloud team to make some of those things happen. I can't tell you there's any guaranteed date on it. But we have a lot of customers that say, I want to do dev test in your cloud because I don't want the capital expense of it, make it operational, but I want to deploy locally. So you really need the same environment. We don't need all the dev tooling, but we need the orchestration and whatnot. Move to that environment and leveraging Power. We have plenty of customers asking for it. It's work to be done with our cloud business unit amongst all the other things they're trying to do. So, any other questions? Most of these, some of these, we have runs with KVM as well as bare metal. We can show you a comparison of that. It's pretty much the same delta between them, but they're all obviously a tad slower because of the extra layer of software. But we do it in both environments. Other questions? Yeah. Oh, I realized I don't have a cost chart in here. So shame on me. It was in the presentation I did across town earlier today. A 2-socket 2U box with the same amount of memory in it as a comparable Intel server is within 5%. Sometimes they're cheaper, sometimes they're a little more expensive. When we talk about the HPC box that has the embedded GPUs in it, and compare that to what I can do with an Intel box, it's tons cheaper. Okay, because we don't have a lot of this other overhead, bus overhead, because of what we've done with attaching that. So the key thing is to understand what you're trying to run, and we work a lot with software providers like Neo, like Redis, like Mongo, to make sure that the right box is the right one to look at. I really thought I had to try to do, but I just had the performance one of 1.8. See, they don't let me talk about price, to be honest with you. I'm serious, and here's why. I'm an engineer. I want to come up with solutions and figure out the best way to do it with a client. What I don't know when I go from client A to B to C is what their discount rates are. So no matter who I talk to, I give them a bad number. Okay, so I don't give numbers. I say, hey, who's your account leader? I'll get them to give you the information you want. It's just because of that. I can't even fathom all the discount rates that exist in the IBM portfolio. But they're similar to the discount rates you will see on Intel lapses. You know, in the 30, 35, you know, depending on models. Sure. Talk a little bit about it. I can't really tell you specifics. We are working with NEO on something that we developed with the Open Power Consortium called streaming. And what it allows you to do is put accelerators in the path of the data through the FPGA. We're working with them to understand which are the ones that give us the biggest bang for the buck for the customer set. And so we have ongoing discussions. It's not anything that I can say, hey, this month you can get one. But there is a lot of discussion about that with NEO as well as other providers. We really want to leverage this acceleration that we can do. We really believe it changes the equation for businesses to drive performance up and costs down. And when we say that, they go, nah, that never happens. No, we're showing that. We're giving real numbers. So it's been pretty exciting. I went from wondering if I was going to get fired and have to retire to, I don't believe it's just cool stuff happening. You know, every day we trip over another environment. Facial recognition, not just with casinos and governments, but with banks, because they believe that's the only way they can prevent fraud of multiple accounts. Is to actually tie a picture to the account. Just tons of things we can stumble across as we talk with different providers and different people that are out there that have been building accelerators in the past, but really weren't commercially
yeah, and then I'll just make sure the last few minutes
because of the overhead they had to do.
follow.
And they're really excited. We have some genomics accelerators that are reducing the time for genomics by several X and manage those things. So it's a really cool environment. It's a fun, as Doug said, it's fun being hardware. For a while, it wasn't really a lot of fun. But it's really fun to be in hardware because of a bunch of these things. And working with all these companies and having these discussions, just tripping over sometimes another idea and say, wait, what if we, well, if we did this, yeah. So those meetings get to be real fun. Other questions, comments, funny stories? All right, well, thanks for coming. I appreciate your attention. And it looks like nobody's going to the sugar coma, so that's good. That's good.